Hello and welcome everybody to the second deep dive day of the TUM.ai Makeathon 2022. If you haven't watched yesterday's talks from Microsoft about responsible AI and from IBM about AI for climate, you can now find the recordings of this on our YouTube channel. And thanks again to Microsoft, Rocher and IBM as well as TNG for sponsoring the Makeathon and making all of this possible. Today's two talks will also be recorded, but I would highly recommend you to watch them live and use this opportunity to get your questions answered by the speakers. For this, please write us your question in Slack channel number 2. Now to the agenda. We got two exciting expert talks for you, followed by the partners launch. Our first speaker today will be Simona Santamaria. She is co-founder of Riva AI, a Munich-based startup focusing on building privacy by design APIs to enable seamless data collaboration without compromising privacy. She will be talking about the topic of synthetic data generation. After the talk, there will be a 15-minute Q&A, so don't forget to ask your questions in channel 2. Then, after a short break at 7:30, we will be joined by Adam Hilbert, the Chief AI Officer at AI for Medicine, a Berlin-based startup that integrates medical science and artificial intelligence to translate data into action. He will be talking about AI for personalized prevention in healthcare. Again, this is followed by a 15-minute Q&A. Then, right afterwards, at 8:15, the partners launch will be happening. A chance for casual interaction between the Makeathon participants, you, and the partners. So if you want to get in touch with our partners such as IBM and TNG to see what they're working on, maybe find a working student job or the topic for your thesis, then be sure to join the partners launch. Now you know what great things we have planned for tonight. So let's get started with our first talk after a short introduction from my side about Simona. Before co-founding Riva AI, she completed her bachelor's and master's in mechanical engineering at ETH Zurich. During that time, she developed a simulator for complex, minimally invasive heart surgeries as part of a student project, interned as a robotics engineer at Amazon, where she created a machine learning powered augmented reality application, and during the start of the pandemic, she co-founded and successfully exited a voucher platform, which won the Female Social Impact Award 2020. So I am very happy and excited to have you here with us today, Simona. And now the stage is yours.
Thank you. I will share my screen. Okay, I hope you can see my screen. Okay.
Yes, because
thank you for the introduction, and thank you for everyone who's attending today. So yeah, I'm Simona from Riva AI, and today I will talk a bit more about synthetic data and especially their use cases in healthcare. AI can be racist, and unfortunately, this is nothing new. By now, we have many examples where this is the case. But especially in healthcare, this is very problematic. If we look at, for example, a detection algorithm to detect cancer in breasts, we see that the performance drops significantly for women of color. And why is this the case? This is the case because the algorithm is trained on female European breast images, mammographies in particular, and they have a different tissue density than Black women. And later I will talk more about lungs and chest X-ray images. And there we, for example, had to learn that Asian lungs have a different density than European lungs. So also there, the algorithm is not able to perform the same for different demographics. And if we talk to people to figure out how they solve the problem, either they're not able to solve it, or they spend up to 6-digit figures to buy data, very specific data from data brokers. The bias problem in AI, for AI algorithms in radiology is not just about demographics. This is actually just one part. Another very important challenge or issue is that you have different different devices from different manufacturers. That for if you go to a doctor who's using a Siemens device, the image is slightly different than, for example, a GE device. And the algorithm is struggling to handle these differences. And the third challenge is different pathology indications. So very rare diseases, for example, are very often not detected by the algorithm. And there again, if we talk to people, we see that if they train their algorithm on their data and then they apply it on real data, which is just different ones, they have a performance drop of up to 30%. And if they then want to tackle this issue, they pay up to 1,000 euro per image, especially if it's a rare disease. We want to solve this problem using synthetic data. And this way we can actually address two different issues. One is what I just mentioned, so that the training data is not enough diverse. So by using synthetic data, you can increase variety in minimizing the bias of the training data. And also you can fill the gaps in the data sets and enrich them synthetically. At the same time, why do we struggle at the first place with the bias? So very often this is because you don't have enough variety in your training data. And it's actually quite challenging to access the training data. And this is very often due to privacy issues, which can also be solved using synthetic data, because this way we can ensure that the data that is at the end used for the algorithm is private. And this way you can then accelerate data partnerships as the hospitals can share their data. And also it's easier to enable data collaborations between third parties. So you have the complement part and also the anonymization part. Here, sorry for that. Here I would like to take a step back and give you a bit more theory about synthetic data, because at the moment it seems quite popular and it's popping up at many different places. And you can distinguish between structured and unstructured data. In the structured data case, if you generate synthetic data, you can use the fact that the data is structured, and that's then much less computationally expensive. In that case, if you look at tabular data, you can work with marginal distributions, variational autoencoders, and also generative models. We are tackling the unstructured data case. As I just shared, we are working with images, and you could also work with audio data, which is quite similar, especially when talking about the feature space, which is basically the transformation that you use to then train your models. There you can work with in-painting, variational autoencoders, generative models, and diffusion models. And I will talk more about these techniques later. This is how our pipeline works. So you can imagine, or it's not just imagining, but it's really how we do it. We take original data, we input this original data into our synthetic data engine, where our algorithm is learning the distribution of the data and the features and so on. And this is then how we generate the synthetic data, which is anonymous and balanced. And this is then fed into the AI models. For example, the detection algorithm for breast cancer. We are working with two different approaches. One is generative deep learning models, and the other is deterministic abnormality insertion. The first one is also quite known under the term GAN. And here I show an example of X-ray chest X-ray images that we generated using a GAN that I will explain in the next slide. In the second part, on the bottom, you see how brain lesions were inserted into an MRI image. We call this approach in-painting, as you basically inpaint a lesion into a healthy image. But I will also explain that more in detail later. If we look at GANs, I would like to quickly explain on a quite high level how they work, but also later in the question session, I'm very happy to go more in detail. They are two-folded, so they have the generator and the discriminator. The generator is the part that generates these fake images, and you input noise, which is really just black and white images or zeros and ones. And from that, the generator tries to generate fake images. The discriminator is kind of the police of the model, and he's trying to distinguish whether the image is real or fake. And you do this backpropagation till the discriminator is not able to detect whether the image is real or fake. And we do a conditional approach because we also add the class. As I just shared the example with the cancer case, there you need to, at the end, you want images that have either cancer or no cancer, or also like images with pneumonia or no pneumonia. And that's why it's very crucial in healthcare and especially in our applications to add the class. Another very important characteristics in healthcare is the high resolution, as later on you want to test your images, really giving them to radiologists that they have to compare, for example, real and fake images. And chest X-ray images are the quite high resolution if they're real. So it's very important that also the images that you generate are the high resolution. And you solve this by using progressive growing. So in that case, you feed in a 4x4 image, then a 8x8, and so on, and you continue the training. So as you continue and feed in high resolution images, you can imagine how the model is able to learn more details. Also maybe interesting to mention, as I just talked about the case in the left, here I show an example of X-ray images of COVID patients or no COVID, but we are working with a GAN model that is actually working with 14 different labels. So not just COVID, but also pneumonia, cardiomegaly, and so on. And it's actually really interesting to see how the model is performing, like generating synthetic data much better for specific cases. And that's also where it's very interesting to then see where for different pathologies, sometimes insertion is more interesting and performing better, and sometimes deep learning models. And at the end, I'm quite convinced that a hybrid solution will be very promising. Okay. Next, I would like to share a bit more about our insertion idea or technique. So there at the bottom, you see how we take an image of a healthy lung. Again, it's a chest X-ray image. We do a rule-based masking, which is then like deciding where the tumor should be added. But at the beginning, you just take out a specific part. Then we add the tumor mask in a GAN-based approach. So just the method that I shared, where you would use the generator to generate completely new images from noise. In this case, the GAN is learning how to insert the tumor nodule in a way that the discriminator is not able to detect that it was just inserted. And the tumor mask itself, you generate taking images that have a tumor. You have an extraction algorithm to get the tumor mask. And then here again, you use a generative model to generate more different tumors. So this is also very interesting because very often you don't have enough variety in your data. And by learning or generating different tumors, you're able to generate much more variety. And of course, it's rule-based so that you're making sure that you don't generate tumors that would not exist in real life. Mm-hmm. And also with the rule-based masking, here you can add that the tumor should only be added at reasonable places. So these are the two methods. Maybe I quickly go back to this slide again. These are two methods that we're looking at the moment, but actually the field it's really impressive and inspiring how much the field is changing at the moment. So actually just this morning, I spoke to someone who just like a researcher who published a lot of about synthetic data in the healthcare space. And he just shared that he's now moving from GANs to diffusion models. And it's actually a shift that we see I'm seeing as I talk to many researchers in many cases. As there's a very interesting paper who was just published this year, actually several ones about diffusion models, which are a bit a different approach than the GANs. And they seem to be quite promising in their results. And as GANs have some challenges, they seem to solve those. And of course, at the same time, they also have new challenges. So I'm also happy to discuss this later in the question part. But yeah, I found it quite interesting to see how much it's going on in the field at this moment. And what we're doing is also like research projects with universities, because even though we are a startup, or maybe even especially as we are a startup, it's very interesting and important for us to collaborate with researchers, universities, to really prove our methods and especially also our results. And here, that's exactly what I also want to show here. So this is like a small POC we did, where we wanted to see how much we are able to increase the performance of a classifier, adding our synthetic data. In this case, we worked with chest X-ray images, and the goal was to train a classifier who needs to detect whether an image has pneumonia or not. The accuracy of the algorithm only trained on original data was 77%. If we purely train on synthetic data, it was a bit less, 76%. But the very interesting case was when we add original to synthetic data, where we were able to increase the accuracy by 5%. And also here, with the research we're doing, it's very interesting to see where is really the best sweet spot of how much synthetic data you should add to really increase the accuracy of the classifier. In this case, we used the river again, and the classifier was just the CNN. Beside accuracy, I also mentioned, or I talked about bias, and very often this is a lot of also about the edge cases. So in a hospital, like maybe you have a rare disease of a patient, and it's also very crucial to not just check for the accuracy overall, but to really see how well you perform in edge cases. And that's why we do some further matrices and analysis. In this case here, I show the AOC plot, and you can see that the purple curve, which is the combination of original and synthetic data, is performing the best. And on the right side, I plot the specificity, sensitivity, and so on. And here in red, I marked specificity and sensitivity, because especially in healthcare, it's very crucial. One, it's very important that you check of the people that come to you and are actually healthy, how many of them you think, or the algorithm thinks, that are having a disease. It's important to see how often you're wrong. But also if you're thinking that someone has a disease, but actually is healthy, usually after some screenings, you're able to detect that, no, actually the person is healthy. So much more crucial is the sensitivity. In that case, it's how often that a person is coming and has a disease, but you're not able to detect it. And that's very crucial in healthcare. But if you look at the different plots and matrices, we see that the original plus synthetic combination is performing the best over all matrices. And these are the kind of POCs that we're running at the moment, also with different, like not just X-ray, but we're also looking at CT and MRI. And it's very important to check how the synthetic data is performing. And beside these POCs, we have to run different tests, as it's quite a new field, and also for us to really ensure that with the synthetic data, we are representing original data. We do this with 3 different approaches. One is statistical measures. So for example, the FID score. So you take the original data and the synthetic data, and you're really looking of the distributions of the data, and also like FID score is like a distance measure. So you really check how much the synthetic data just statistically is representing the real data. In case of model performance, that's what I just shared, is that you really train an algorithm like a classifier on original data and on synthetic data, or also the combination, to see how well, how much the performance is changing. And also very crucial, if the classifier is actually really learning the disease and not like something else. Doctor evaluation, that's exactly why we do the progressive growing. So here it's important to really show the images to the doctor. They should not be able to detect that it's a fake image, and they should still be able to see the disease in the image, for example, so to detect the right label. And for this, we're running different tests. Another issue besides quality assurance is the privacy, as you really want to be sure that you're not leaking information. As I explained the generative model, it's the generator who's generating the images never sees the real image, but still you could argue that by doing a lot of propagations, at some point, maybe some information is leaking and the generator is like not holding the privacy of the patient. And that's why we do privacy attacks. So what you do is you look at the synthetic data and you do privacy attacks to try to reconstruct information from the original data. And also you compare to the original data where you check for singling out, linkage, and inference. And yeah, this is important to really assure that the privacy is holding. I already shared that we are doing research collaborations with universities. This is really purely about proving and seeing how much, what is possible with synthetic data and what use cases are especially interesting. At our business model at the end works that in a way that we're collaborating with clinics that are more like our partners, and they are they are providing us the data that we use our generative models and also the in-painting methods on-prem on their side. So we never see the original data. It's really working on their software. And then this way we generate the synthetic data, which is then private, anonymized. And this is can then be used for our customers at the end, who are AI innovators. So we're mostly it's medical AI startups, established medtech companies, and pharma. Now I talked a lot about synthetic data applications in healthcare. I find it quite interesting how, actually how this is, it's also used at many different industries. And this summer, I was at 2 conferences talking with many people about their use of synthetic data. And what I heard a lot was gaming, so that you generate realistic gaming graphics. Another approach is autonomous driving. So you use synthetic data for data augmentation and also adding different perspectives in the different environments and so on. Especially in autonomous driving, the people I talk to, what they, for example, do is they have a video of a car driving that they use for learning, but it's beautiful weather. And then they add rain to the images to have more training data in cases where it's raining. And they do the same with fog. And it's the same weather, how they add weather. I actually had also a very interesting conversation with someone working for military, where it's also very important that their computer vision algorithms are able to work when it's very foggy. So they add fog to their images. And all of them are working with different methods. And And I guess that's also one reason why synthetic data is quite popular at the moment and pushed a lot. So it's not just about healthcare, but it's also about other different areas. The third part is internal software testing. So very often you, as I mentioned, you have your training data, then you train your algorithm, and you have your testing data, and then you ship it to production. And then at the end, it's again used in real life with like different data. And very often you have this performance drop. And in this case, software testing, we talk to many potential customers who just need more validation data or testing data. And in this case, one application was where you have your phone and you don't have enough data of people speaking in the phone in order to be able to minimize the noise when someone is talking. So they asked us if we could take this voice recordings, and if you could generate more by using synthetic data, so that they have more variety in the noise that they use to test their software algorithm to decrease the noise when you talk in the phone. So many various different applications, and also later in the discussion, I'm happy to talk more about this, or also hear your ideas actually. I talked about River, who we are. It's at the moment we are mainly 3 people. Yeah, I'm mostly responsible for really the AI part. I'm really training these algorithms, looking at CT, X-ray, MRI images. Kati is my other team member, also in technology, and she's mainly focusing on all the parts around, besides just generating these X-ray images. So really how to then use these generated images for our customers. And Jonas, he's our business guy, responsible for everything besides the technology. And I'm also showing this because especially from next year on, we will look for working students for actually different projects. So if you're listening to my talk and you find it very interesting, please reach out to us. You can write me an email. I'm very happy, or we are actually very happy to talk to you. We already had several interns. As we also have university collaborations, we were part of different lectures and projects. And yeah, we really like to work with students, and yeah, would be very nice to hear from you. And I guess that was my presentation. Thank you very much.
Thanks so much, Simona. A very interesting talk. And at the end, you mentioned, okay, there are positions maybe available as intern or working student. What are you looking for? Are you looking for bachelor students, master students? Can anybody apply, or do they already need to have some experience with GAN or something else?
Yeah, good question. I actually talked to my colleagues before to be sure that I'm sharing what we need. And we're all agreeing that it can be quite diverse. For sure, on the AI side, I can always, I think I'm there would be a lot of learning opportunities for the students. And also it's for sure nice if they already have some AI experience, but not mandatory. But then as I shared, you also have the whole business side or product side of, it's not just about the generation of the images, but also really the challenges of how you bring them to the customers. And also, for example, now at the hackathon, it's also more about evaluating the images. So there's a variety of different projects that could be implemented, or worked on.
Great. And because you mentioned customers right away, the first question, are you currently just focusing on X-ray images, healthcare data? Or as you mentioned, like a little bit, are you already focusing on software testing and other areas?
Good question. At the beginning, we were very motivated and looking in all directions. And then we quickly learned the importance of a focus. So at the moment, I'm looking at X-ray, CT, and MRI images. So all purely in healthcare. And we're really planning to stay in healthcare at the moment for sure.
Great. And then out of personal interest, how did you get your first foot into the door with healthcare? Because I imagine there are great master students here. They say, okay, we want to do something in healthcare, synthetic data generation. How do you win the trust of the clinic? Or you go to Siemens Healthineers that has connections. How did you get this started?
Yeah, that was actually very interesting because they approached us in all other industries that we were also looking into insurance and finance and like testing of software in general, and healthcare then approached us because of the bias issue and the privacy issue. But it's definitely true that working with healthcare, you have a trust, you have to gain the trust. And that's where we do these research collaborations. Also, like research clinics are very interesting for us, university clinics. But yeah, I guess it's really about proving that it works. Yeah.
Great. By chance, are you already working with the Charité? Because our next speaker is working currently as a lead of AI at the Charité.
Yeah, true. We're not yet working with Charité, but we already talked to some researcher there, and we would for sure be very interested in collaborations.
Great. Maybe you can also use the partners launch afterwards to exchange a bit. But yeah, we have a great question now from Mark from Slack. And what would you do if a privacy attack shows that it is possible to retrieve the training data from your model? How can you improve the model to be more robust against these attacks?
Mm-hmm. Yeah, very good question. One interesting research topic in that area is differential privacy. So how this works in combination with generative models to really generate the synthetic data is that you add noise to your weights. And this way you can, this is one way of ensuring that you don't have any information from the training data leaking. Also important maybe to note here is that very often we are quite afraid of synthetic data and privacy issues, but actually very often how it works at the moment, it's just that they use the whole image and they just remove the name and so on. So at the moment, very often you train on purely original data. And so with synthetic data, you already go one step further than just pure anonymization of deleting the name. But definitely I would say that differential privacy is one way to go.
The patients whose x-rays these are, do they have to say, okay, I'm willing to share my x-ray? Or because the name is removed and it's anonymized, x-rays of any patient can be shared from those clinics?
Good question. It depends a bit on the use case, but usually you have to be willing. And also in any case, you should be able to say that you don't want that your data is used anymore. But it's also true that in case of anonymization, it's again a bit different. Yeah.
Okay. Then now we have a question from Lucas. And since the pipeline needs data in the beginning to generate the synthetic data set, what would be the difference with data augmentation?
I understood the last part. What was the first part?
As the pipeline already requires original x-rays, original data in the beginning to generate the synthetic data.
Okay, yeah.
What is different? Yeah.
That's actually also, I really like this question because I didn't mention this, but very often at the moment, what you already do is you have the original data and then you do simple augmentation, like rotation of the image is a very popular one. And it's true that in our case, we also just augment images, just not by rotation, but by adding synthetic data. So when we check for our performance, we also have to look if we are actually better than pure simple augmentation by rotation. And in that way, it's true that it's actually not much different to the usual pipeline of original data and then augmentation and then training.
Okay, so in that case, we already have the privacy, probably the X-ray image is already private, anonymized, and then it's very similar to data augmentation. Yeah. And on one slide, you showed that, okay, you take a small area, then you take a tumor, change this with some predefined terms, and do you only add to one original image a new tumor, or do you take this image and then add hundreds of different tumors in there, and then in the data set there's like one original image with like hundreds of different, or is every original image only used once?
That's a very good question, and this would just be the perfect project to start with. Because that's exactly one of the examples where a lot of research is still going on. Usually how you would do it is to take one image and then adding the tumor just to this image, and then another image with another tumor to add even more variety. But you could definitely come to me and argue that it's even better if you use the same image with different tumors. And that would be one perfect project where we would set it up and then test to figure out what makes the most sense. And it's really what is going on at the moment, to really figure out the best parameters and set up to increase the performance.
So I don't have a lot of background knowledge with X-rays, but we saw, okay, it's just a small area that's augmented. Is normally the tumor just affecting this small area and it can't be seen anywhere else in the X-ray? Or do we just say it's good enough that we just change this small area and don't care about the rest?
I'm really happy about these questions, because they really show that the people understood what I just talked about. This is exactly where GANs or in painting is interesting to either use one of the two approaches or a hybrid solution. Because there are cases where you just have one nodule, which is kind of a tumor, and there you can really just add this part. But in case that the tumor already spread, you have many different tumors, or even very small ones that research is showing that the doctor doesn't see, but the algorithms are sometimes able to detect those. So also very interesting. And in those cases, you need different approach than just one in painting. So either you could say you try different, like several in paintings, or you go with a more GAN-based approach, because GANs are more like, they are better in generating different like distributions.
Great. So if I understand it maybe correctly, this could mean that in the future we're able to detect those tumors even earlier in the X-ray images and help with the care.
Actually, a lot of research is really showing promising results of how AI can really, really support the doctor in a way that tumors are detected earlier. Yes.
Right.
And this is not just about synthetic data; it's also really about the improvements in the detection algorithms itself.
Great to hear. Then hopefully in the future there's more early detection happening. And in the examples you showed, those tumors, are they already large? Are they like middle? Are they small ones that we saw? What can we imagine? Is it like, it is an easy example to see, and in reality you're working like with way smaller tumors that are even hard to see with your eye?
Yeah, it's actually, I'm getting better and better in reading my own images, like reading an image and finding if it's cardiomegaly and so on. I would say, or what I for sure can advise to everyone in computer science working in healthcare, to really talk a lot with other doctors, because I'm exchanging with them every week, and every time I'm learning so much about how I have to approach it, not just from a computer science way, but also really from a health background. And in my case, I'm like, my background is in computer science, I'm trusting the labels, and sometimes I see the label and I see directly where it is, and sometimes I actually don't, and that's exactly where I'm exchanging with other doctors. At the moment, as we work with 14 different pathologies, really, like, our images are very, very diverse. So maybe the images that showed like bigger tumors, smaller tumors, different, like pneumonia again looks very different, COVID looks different. So yeah, it's not boring at all.
So did you also try it for COVID, or is it just based on like tumors from cancer?
One project with the university collaboration is that they are generating a classifier who is detecting COVID, and we are generating the chest X-ray images for them to add to their algorithm to increase their performance. And then another research project is about what I showed with the brain MRI and adding nodules, so adding tumors to the brain. So yeah, different projects.
Great. So we're already getting to the last two questions. One is, again, a bit clarifying. Is river, or is it pronounced river or river?
River.
River, okay. Sorry for the mispronunciation. But yeah, is it only for generating image data for now? Are you also planning to do tabular data and other data in the future? And maybe what was why did you decide to start with image data?
I would like, for now, definitely healthcare, because we just really see the potential and also the importance. If you look at the bias issue, at the privacy issue, and now I talked a lot about radiology and X-ray, CT, MRI. You also have pathology, which is very interesting. And in both areas, you have more and more algorithms being developed. So I think for now, it's definitely healthcare. Yeah, I would definitely, I guess my two colleagues would agree. The other part of the question was why health? No.
No, if you can also generate tabular data, and maybe in the future you are planning to go in there.
Tabular data, it's, as I mentioned, you usually you use a bit different methods, because you use this structured, the fact that they're structured. So sometimes it's not even a deep learning model. So it's not really our domain knowledge. What is interesting in the future, and I also talked with the research today about this, is using the report of the patient in combination with the generation of the image. So you take the real image of the patient and the whole report, and then you're able to add even more labels and even more features to the synthetic image that you're generating. So in that direction, yes, but not that I'm very sure that like we're not going into tabular data.
Okay, and now another question from Lucas, just about the privacy concerns. Again, the original data going through the pipeline is already anonymized.
Yeah, yeah.
Yes, perfect. And now another question came in about the performance, the accuracy that you showed. You showed the original data set, the synthetic, and then a combination of the two. If this person understands correctly, it means there was always one model trained on this data. So it's not an ensemble model of like the original and then of the synthetic data. So they're asking, have you also tried making like an ensemble where you have one model just on the original and one just on the synthetic, and see if this would improve performance even more?
If I understood it correctly, you would mean that you train on original and then like pre-training on original and then continue training on synthetic?
No, how I understand it, they mean two different models. So one just on original, one just on synthetic, and then just use an ensemble method to see, okay, what's the result out of those two models?
Because what we did is purely training on original and then purely on synthetic. That's what we did. And then on the combination of both.
Okay. So I think the answer to the question is exactly that it was trained on the combined data and it was one model and not two separate. Okay.
Yeah, it was like how we set it up is, yeah, to train on only original, then to train only on synthetic to see how that works. In some cases it works, in some cases the synthetic images are not representing enough. And the most powerful is if you add original and synthetic in the training process.
Great. I hope this cleared the question. And just a reminder for next time, please don't DM me the questions, you can always write them in channel number 2, and then I will also be sharing your name when asking a question. And thanks you so much for joining us today, Simona. I hope you enjoyed the Q&A, and later at 8:15 there will be also the partners launch. I'm not sure if you will be joining, but we would be happy to have you. Maybe some of our participants are interested in working student positions, as you mentioned. And yeah, thanks so much.
We will be there from River, and really thank you for the questions. Usually they're not this technical, and I'm very excited to get these technical questions and to see how you really understood my presentation. Thank you.
Great to hear. Then now for our audience, we will now go in over in a short break of about 10 minutes. And then at 7:30, we will continuing with the second talk, also about the topic of healthcare, with Adam from AI for Medicine. And the topic will be about personalized care through artificial intelligence. So looking forward to seeing you at 7:30. See ya. Welcome back to the Deep Dive Days. I am excited to now be joined by Adam Hilbert, the Chief AI Officer at AI for Medicine, a Berlin-based startup that integrates medical science and artificial intelligence to translate data into action. He will be talking about AI for personalized prevention in health. And now a short introduction about Adam. Before joining AI for Medicine, Adam completed his master in artificial intelligence at the University of Amsterdam, worked on deep learning for outcome prediction of stroke, co-founded Novum AI, which developed deep learning algorithms for digital pathology to support the stratification of different therapies for cancer patients. Then he joined the Charité in Berlin as a machine learning scientist, where he's now leading the machine learning team in Charité Lab for AI in Medicine, the so-called CLAIM. I'm very happy and excited to have you here with us, Adam, and now the stage is entirely yours.
Thank you very much for the intro. Yes, it's great that you also introduced a little bit. I already forgot about my previous startup experiences. It's always nice to hear back. So right now I would like to present you for small Berlin-based startup, AI for Medicine, where I'm Chief AI Officer and have been working with the company for a good 2.5 years. We'd like to show you a quick intro about the great team that we have here in Berlin. I highlighted myself and Pooja because we are the two people who will be with you throughout the hackathon and support you also. As you might have seen as well, we are setting a challenge for you in the AI for Health or AI in Healthcare track, and we'll be very excited to see teams competing on that and solving the problems that we have proposed. So we both with Pooja have a strong technical background. We're coming from computer science, AI. As already introduced, I mostly worked in medical imaging and deep learning for stroke in my academic career so far, and Pooja has been working also with medical imaging and GANs, and in AI for Medicine, she is our absolute cloud engineering expert. Just a quick run through or other members of the company. Dietmar Frey, who is our founder and CEO, who is a board-certified neurosurgeon and still active in academics and research, not in the clinics anymore, founded AI for Medicine. Tabea Kossen, who is, funny enough, just tomorrow is defending her PhD thesis about GANs in medical imaging, so I could really relate to the previous talk as well. It was great to hear about the other efforts as well in GANs. I'd like to also introduce Vanessa, our business expert with vast experience in the industry, and Vince Madai, our absolute, I call him the Swiss Army knife advisor for AI for Medicine, because he is not only a medical doctor and medical AI researcher, but also an ethicist, which is becoming really, really important in the work of AI for Medicine as well. So in the following, I would like to give you a little bit of an overview about our vision, how we utilize this great multidisciplinary team coming from AI, but also from the clinics, from medical background, and how we identify the current and today's challenges in preventive health and in digital medicine, and how we go about them, how we tackle those challenges. So first, I would like to ask a little bit of thinking about from you about what is the first thing what pops up in your mind when you hear AI in medicine, AI in healthcare, or medical AI. I think most of the people think about clinical decision support, and there is nothing wrong with that. I would also do the same, because that's also my research interest as well. But basically, this predicament means that, but when we talk about AI in health, we a lot of times think about doctors treating patients in the clinics, right? We're thinking about AI models that help them coming up with a decision or asking for a second opinion or augmenting that decision in a way. Now, this means that we are already in the hospital setting, right? There is some sort of disease, some sort of illness or an adverse event happening to someone who is then dependent and reliant on care, and there is a doctor who is treating him or her. Now, most of the severe illnesses, of course, don't start in hospitals, right? Where they start as somewhere else, long years before it comes to any hospitalization. For example, I can give you my research background in stroke, long history of, for example, diabetes, atrial fibrillation, or any vascular disease in many years can result in an actual stroke, which is, of course, a devastating event and can easily imply really severe complications and bad outcomes for the patients. So these chronic diseases, as diabetes, atrial fibrillations, actually develop in many and long years and might only cause some severe illnesses 15, as we can see in average, 15 years later they pop up. One of the most pressing problems in health is means that chronic diseases could actually be prevented and could be handled. And there are, of course, solutions for this in preventive health, so-called disease management programs as well, but they don't seem to be very efficient. Again, coming back to the stroke example, in stroke treatment in the last 5 to 10 years, there were major improvements in the actual treatment of stroke. Yet, when you look at the statistics and averages throughout also in Europe or US or globally, you see more and more strokes happening to people. Yes, we might be able to treat them better, but still there is the increase and rise of these chronic diseases and adverse complications. So what we identified in AI for Medicine by also talking to a lot of customers and a lot of players in this sector is that the current prevention strategies, the so-called one-size-fits-all, is highly inefficient. What this means that for stroke, for example, smoking, alcohol consumption is a risk factor. So what we might call as a prevention strategy is that we just advertise that everyone should take down the cigarettes and consume less alcohol. This is an easy solution to scale, right? We can spread the word, we can advertise this. However, it might not be that efficient as we think at first. When you think about the individuals who really have some chronic conditions and diseases and want to prevent a stroke, they might think that I'm just hearing this from everywhere, right? Smoking is bad. And they are not taking it seriously. You could also not take it seriously because you think that this is just the common sense. And yes, we should live healthy. So what we see as a problem is the lack of personalization and the lack of individual touch to what are the actual person's risk factors to prevent a stroke or other adverse illnesses or diseases. With this prevention strategies that we are seeing now being implemented, people are not that engaged. They are not motivated, and they also, to be honest, don't understand many times what are these chronic diseases, how they work, and where they could lead. This means all of these strategies force people to rather handle their health reactively, right? Go to the doctor when they are already sick or where there are problems or where they really rely on dependence and treatment, rather than thinking proactively and try to prevent problems before they arise. Now, this is exactly what we want to change in AI for Medicine. Our goal is to personalize prevention by empowering patients and also patients. I should say empowering people because they might not be patients yet. And of course, we are doing this by using AI and building on our multidisciplinary expertise on understanding the medical background and the AI background as well on this, but most probably focusing on the people who need to prevent their disease. we're trying to lower this immense burden from chronic diseases and reduce prevalences of adverse complications such as stroke already mentioned. By empowering patients and better guidance and understanding for them, we aim to fill this lack and unmet need for chronic disease patients as well, where they simply feel left alone, they don't understand their disease and don't know what steps they should take and what actions they should take to prevent various severe complications. How we aim to do this. Here I would like to go or give you a little general overview on our concept and our thinking. And since I know that you are all interested in AI and the technical background, and I also like that, we are then from here on trying to go a little bit deeper and deeper into how we solve actual problems. So first, the general overview is despite you have seen our team, we are quite heavy on the AI side. We usually don't start at the modeling. And I find this a very crucial point in our work, that we always start at defining use cases and defining the, I now put here on the slide, business needs, but ultimately the needs of customers and users and these people I've been talking about. We start from the data. We understand what data might be available and might also be feasible to use. What I mean there is that if you think about an AI model, for example, predicting the likelihood of a stroke, you cannot ask any user to enter 50 or 60 different variables and life conditions or medical history or so, and still think that your application or your solution is usable, because it's just, yeah, those users are not going to use your application. So you have to think about what is actually feasible to achieve our end goal. When we already defined these use cases, so we know, for example, for chronic diseases, we know that we want to give more understanding about the progression of the disease or reduce dependence and give more insights about the risk of severe complications. When you think about infectious diseases, another use case, for example, COVID-19, you can think about simply the use case being alerting people when they are infected so that they can act, they can understand why they would have such symptoms as they are having, and maybe they can also prevent spreading of an infectious disease. When we already have these use cases, that is when we go to this next stage, where we can utilize the most or domain expertise. Here meaning, again, the AI modeling and the clinical background what we have. We are here asking questions. What might the user want to know about the disease, right? And with this, we can set up a couple of hypotheses, and we can test those hypotheses. Will this work? Can we develop an AI model that answers these questions and extract this certain information that we are looking for and the user is looking for? So when these questions are already answered, then we go into modeling. Of course, we look at the literature, always coming from science. We always do a nice literature review. We check what models already exist, what we might be able to use. And then we go into the modeling and build potentially an AI model that can not only give the information that we are looking for in terms of a prediction or estimation or regression, but also is equipped with additional perspectives such as explainable AI and enhanced usability, so that the patient and the users not only get some quantitative results, but they can also be guided towards what could be the action of that they have to take with the suggestion of this model. So next, I would like to narrow the focus a little bit down. So this has been just a really general workflow that we are following in building our solutions. Now we can a little bit look into how we do this for prevention. You can see here in the middle lane that we basically center two layers of potential solutions around our domain expertise and what we really know, what we can do. Called here AI for medicine intelligence, or layer of that. These two layers are both centered on these expertises. And first, let's talk about the top one. So we think that achieving personalized prevention, first, we have to engage with the actual users. So this is the layer of engagement. Here, we directly approach people through, for example, mobile applications for prevention, and provide them this enhanced understanding of their risk, the disease, and also their causes of actions with, again, usability and explainability on everything what we are building. Now, this is no surprise, no strange or new approach or use case for anyone to build, but I would like to highlight here that this is a little bit of a workaround of the healthcare system, right? We are still talking, for example, about stroke, really serious disease, and that can have devastating complications. And here we are talking about a solution that might not even involve doctors or any health institution, right? Still, we believe that this is one layer of solutions that we can build and that we can approach the user with. But to feel like what I just explained, we are thinking about another layer of possible potential solutions as well, which is the layer of health insights, data-driven or AI health insights. Here, we approach healthcare institutions that basically can enable us to scale better and distribute this notion better. And here we need to implement AI-based diagnostics and insights for the given, sometimes legacy and sometimes older systems of these healthcare institutions. What an example, again, going on the stroke line, could be here approaching insurance companies, where a lot of people are, of course, connected and insured by the company. And with these AI-based diagnostics, we can offer better stratification and recommendation for these prevention programs that I mentioned in the very beginning of the talk. Here, our goal is, so this is when you, I can reflect to those not coming from a technical background, but a little bit from a business background as well. So this would be a B2B2C scenario, right? Here, our goal is, with this better certification and recommendation system, to change this one-size-fits-all strategy into personalized support for these institutions. Now, next, I would like to show you one concrete example that we have already built for the first layer, which is the Health Advisor. So the Health Advisor is a product of AI for Medicine, and it's a stroke prevention mobile application. The Health Advisor can take the user's data, as you can see on this small screenshot. For example, the amount of exercise done per week, the smoking habits, drinking or alcohol consumption habits. The AI model sitting in this application then is able to estimate the likelihood of a future stroke and projects that into 1 year, 5 year, 10 year, so that the user can see what actually the future trajectory of a stroke could be. What is very important here is, again, coming back to this usability, is that the UI not only visualizes this risk, but also offers an interactive way of learning about this risk. So, for example, you can see this small weight slider, which indicates the change of exercise done per week. With this, dragging this back and forth, the user can a little bit simulate and play around with how the actual stroke risk would change. Of course, this is not an immediate change. It's not going to be less likely to get a stroke tomorrow, but in 1 year or 5 years, you can see. So right now there are 3 variables here shown, but you can also see a smartwatch, because we are also thinking about different tiers of this application, where we can integrate smart data, heart rate, steps automatically from any health kit basically available on smartwatches, but it's also possible, it will be also possible to connect to, for example, insurance companies and pooling electronic health records data, which all, as you know, also from a data and AI background, all of these additional data give more and more dimension for the user to understand the sources of the risk and find the these actionable results, what they can actually implement in terms of behavior change to prevent a stroke. This little gamification with the interactiveness, we are still working, but this we believe that ultimately leads better success to achieving some goals and providing this understanding and insights for the actual users directly with this mobile application. So one example for the first layer that we are working on, but how would we do this in a bigger scale? Here I would like to show you one solution and a slide with a lot of steps. I'm sorry about that. Ignore the right part. I will walk you through this little architecture graph. So we are currently developing an AI service platform. Now again, anyone who has built an AI model or even such an application with an AI model, a UI, maybe even thought about, of course, very importantly, data privacy, information privacy. You know that such applications have a lot of the same building blocks, basically, that you have to customize and put together to get such an application. So we also identified this, and as coming from research, we like and love recycling and like to use existing solutions more times in more products, in more solutions. We came up with this platform idea where we can actually, if you look at the top, we can also serve both of these potential layers of solution to achieve personalized prevention. We conceptualize these building blocks, and with this also for users or customers, for example, institutions, it's possible to use existing AI models, as you can see from our AI model library, attached with, of course, the important data governance policies and the trustworthy AI methods that we are using into some business service dashboard that is then deployed in the, for example, insurance companies' own legacy system. So these core AI services are surrounded with all sorts of APIs that we call business data and external APIs. They are not the most interesting in this. One more notion that I would like to introduce you here, if you look at the bottom, this platformization or thinking about modular building blocks for such solutions is not only important from the modeling point of view, so that we are using models that have already developed some time, but also from a data point of view, right? So with these solutions and also unifying data representations across solutions and across data types, we can build on existing public data, but we can also build solutions on existing user data, for example, where the users already consented to utilizing that data coming from smart devices, for example. But the same is also true and valid to customer databases that we have sometimes on. So again, so far, we are going a little bit deeper. And as next, I would like to show you a couple of challenges that we have to face when it comes to developing the actual modeling. So these are challenges that we have to face in medical AI development in all sectors, I think. So first, when you think about and when you do actual medical AI, I think most probably anyone who has already done this knows that this is not your usual textbook AI case, right? Data is scarce, most of the times then sensitive. So you have to think about data efficient modeling. You cannot just build huge models with millions and millions of parameters and try to still achieve some sort of performance. You have to think about the exactly suitable model, you have to think about synthetic data. And I'm really thankful that we had the previous talk. I don't have to talk about that more. And all sorts of different perspectives come into this medical AI development. Medical domain is also a very active domain, which makes it very unique, I think, and also sometimes exciting. That when you deploy an AI model in, for example, such an application as the health advisor, you have to think about model staleness, right? That models expire after a while. As coming back to the example of insurance data and insure people change their insurances. They might go to another company, and then all of a sudden, with the same insurance company's system, you have a drift, you have a change in your distribution in your population. You have to monitor this, and you also have to equip your tools, your model, your framework with solution and processes to update these models. Also, the importance in medical AI, we're talking about prevention, so this is not very directly lives on stake, but we're talking about stroke prevention. So in preventing the progression of chronic diseases definitely can lead to saving lives and lives being on stake with these solutions. We simply cannot think about black box solutions, right? We have to think about explainability, trustworthiness, with all sorts of different concepts coming in here. Here, I would also like to thank the yesterday's talk, which I also very much enjoyed about responsible AI, because this is also a concept that AI for medicine absolutely builds on. We have to go through all those important pillars, and for every solution, we have to tick the boxes and validate our solution that we are transparent, we are explainable, and we are also usable. Usability as the last point here with a twist. I put this on this slide because I just wanted to highlight that in many, many cases when developing AI in medical data, you again have to think about this general workflow. You have to start from the data, and you might not be able to implement and utilize the newest and coolest AI models and tech in your solutions because there might just simply not enough data and your solution wouldn't work. How we go about this, solving these challenges and thinking about these challenges. So we actually identified and thought about this instead of gathering a good set of toolboxes, which already take one of those challenges that we might face in the future. We at AI for Medicine try to elevate this into really infusing all of these challenges into our everyday thinking and into our values. So I've put a short summary about our values here, which every member of the company is actively thinking about, and we are also trying to implement in every solution that we are marketing, that we are building for users and customers. Next, I have two more, a little bit more technical slides. Again, please ignore the text. This is also a little bit more explanatory slide. I would like to here highlight the second option to solve these challenges faced by medical AI development is that because of also this activeness or active property of the domain, you simply cannot think about developing one AI model, right? So we are thinking about AI models living in these life cycles. And this cycle usually in medicine never ends. So we are building models in such a framework where every single step from data cleaning, structuring, preparation, but also understanding, infusing the research knowledge that we have and that we get from the literature is every stage is quality assured. Every stage and every output after a stage and phase is verified, is validated. We do this so that we can catch any error basically as soon as possible. But also very importantly, when you think about that, think about, for example, privacy. when we are deploying a model and building that model on users' data where everyone has consented to use, we have to follow, for example, GDPR rules. So when there is one user for you that withdraws their consent, then you have to know something about, you have to do something about that. You have to think which data went into this model, which model is deployed in the application, and how you update that model to be again compliant to the user's consents. And hereby I would like to show you some actual examples how AI for medicine solves such challenges. So building our platform is right now happening in Google Cloud. We are using Vertex AI for developing the models for traceability. In the previous example that I gave, we are using data versioning control. Of course, GitHub everyone is familiar with, but we are using also model versioning, which is available in Google Cloud, but I think most of the cloud providers. We are building models mostly in TensorFlow, in PyTorch as well. And for trustworthiness, I didn't change this slide after yesterday's talk. We so far have been familiarizing with the IBM Trustworthy AI framework and TensorFlow Responsible AI. But I'm actually very, very eager and excited now to look into the Microsoft Responsible AI as well, because I to be honest, have not dig deep in that yet. These are both very useful tools, and there's plenty of research and actual tools that you can use to build trustworthy AIs and learn more about your methods, models as well, but also to be able to offer more for your users. Yes, and in our CI/CD pipelines, we are using MLOps concepts. Last slide, just a quick wrap up for also customers and partners we have worked with so far within AI for medicine. To improve personalized health, we have so far had projects with pharma companies, insurance companies. You can see on the left side that all were actually great opportunities for us to learn about the needs, the challenges that we might face in this sector, and also to test a couple of solutions how we can improve actually personalization in preventive health. We, as you have also seen from the team, we are an AI team basically, so we are not very experienced and we are not building software. So that we are working with tech companies as well. The Health Advisor application that I have shown to you was built by a IBM daughter company based in Berlin, IBM iX, which we have great collaboration with, and we have done multiple projects as well here, and we are participating in the Google for Startups program from the summer of this year, which gives us great resources also for building our platform in Google Cloud. So I hope I could raise your interest in preventive health and give you a little bit of insight how, at least in AI for medicine, we are using AI for improving personalization, and I'm really happy to hear any of your questions, and thank you for your attention.
Thanks so much for the interesting talk, and great to hear that you could already take something away from our deep dive days yesterday with Microsoft. And so let's start with a bit more general question. You mentioned that you are starting from the use case, from the business. And this person is asking them, how do you know that the use case is possible, feasible, and not just a moonshot that you might not be able to reach?
Yeah, very good question. I should have put not the first step there, but the 0 step is basically do this with partners, with customers. So usually in our previous projects, how we identified these use cases was to go to the customers, go to the users, and identify their needs. And then you already have a validation that this is at least the customer need, customer pain that you are solving. And throughout the journey, you might identify that the solution and the use case that you are developing might not scale that well, right? That maybe we are only solving a really specific challenge here, but that's also a learning experience. So you can take that with you, and in the next project, in the next application, for example, that you are planning to build, you can do something differently. You can change some perspective, a little bit broaden the scope or something like that.
Has this actually happened to you, that you said, okay, this use case is interesting, but we're just not able to get with the accuracy there? And if yes, could you share a bit about that?
Yeah, that's a good question. I try to think back. I will strategically, I will not answer that question because I could answer that question, but I would give away a couple of things for the challenge that will be announced tomorrow. Yes, but very, very good question.
Okay, that will make everybody even more curious about the challenge. Maybe this is the problem you were not able to solve, but our participants might have a great idea. And then a bit more general also, they're asking what solutions are already live or what is close to being live.
So as you have seen, the Health Advisor application is very close to be live. So we are doing some testing of the application from different perspectives. We have built other prevention applications as well. Again, I will not disclose before tomorrow's challenge what that might be, and that's also close to being live and being in the same testing period. And so far, these are the closest solutions that we have, being live or being out on the market, basically. And so give a little bit more insight to that. So this is the sort of application line, right? So the first layer of solutions that we are thinking about. But we have with AI for Medicine in the last 1-2 years, we have also had various projects which were more like data analytics as a service projects with these different customers that we had. Those resulted also in solutions, but less in solutions, in hands-on solutions. So there were no applications, for example, as a result as a product. For example, we mentioned pharma companies with Bayer. We also had quite a big scale data analytics projects where we have found quite nice insights into some trial data set, then drug development trial data sets that then resulted in some internal solutions for them, but we were not partnering up for bringing that further because that's simply not out of our scope.
Yeah, thanks. And I completely understand. Now a bit more in depth. And one person is asking, how can you detect that the model expired or that it drifted?
Very nice. Yeah, that's a very cool question. And so this is quite a hot topic in research as well right now, just because of the fact that more and more medical AI is developed and hopefully and luckily is deployed and used in clinical practice as well. So first of all, I would always start from what is easier is detecting data shift, right? That you're looking at, you always know with the data versioning, with the model versioning, you know that the current model that you have deployed, what data is it based on? You can draw some statistics, you can look at different distributions of dimensions of your input. And with any upcoming data, you can develop and you should monitor running statistics, and you can see how the actual statistics of the last, 50 predictions differentiate from those that you use for training. So this is more recognizing the data shift. This might not, in most of the cases, mean that your model is becoming less applicable, however. So identifying that model is expired, so to say, so the predictions are not that useful anymore for those for the future population, basically, is taking this one step further. So then you should understand what these different statistics and the distributions are differing in. So with this, you can identify some areas, some maybe subgroups, or sub-statistics in your input that simply make the model will be harsh, fail, or predict nonsense or something like that. Then you can already know that in what perspective the model is expired, and you can think about, for example, augmentation, drawing different synthetic data or sampling synthetic data to solve this kind of lack of specialization of the model to this new population.
Great. And at the end, you showed a bit about your ML life cycle, for example, that you're using data versioning control and others. And here we have someone asking themselves, they're using a Kedro and ML flow. And if this is like a good solution, or if they should also switch to the data versioning control and the tools that you showed on your slide.
Yes, nice question. For a while, we were actually in quite a struggle figuring out what tools fit together, because MLflow can actually do a lot of stuff. So it's definitely one of our favorite tools, and we are also using MLflow for like experiment tracking. I think the answer so I don't think there is good and bad, right? I think it's a question what fits your needs and the actual use. And in AI for medicine, again, at least for now, it might change next year. I don't know. We found a good combination with using MLflow for experimentation and data version control next to that. But I also have to add the notion that not only MLflow knows a lot, but when you are developing AI in the cloud, there are a lot of things already solved, right, in the cloud, and you might not need that many external tools to augment your workflow.
Great. And this question is about explainability, and they're asking themselves, how do you make the model explainable? Is it sharp values? And you also mentioned explainable and trustworthiness. So they're asking, what is trustworthiness? So what's the difference between explainable and trustworthiness?
That's great. I dropped too many buzzwords. No, this is a great question. So trustworthiness is, and I wasn't sure. I wasn't actually sure what to put on those slides, because this is also a really developing topic and really open research right now. So trustworthiness is a little bit a broader perspective, right? For example, explainability is part of trustworthiness. And here I mentioned explainability because that's something also for AI engineers and scientists. This is something that you can immediately grasp. For example, with solutions as Shopify use to not really to make the model explainable, but to make your predictions explainable. This is with the so-called post-hoc explanations. So yes, we are working with sharp waves, for example, to explain predictions. When it comes to tabular data, works great. When it comes to imaging, as for example in the mentioned pharma project, we have been working with MRI imaging, and we are using different saliency maps, GradCam, smooth-grad, these kind of methods, layer-wise relevance propagation, to get some insights into where the developed models look at the imaging. And yeah, so this is the post-hoc explanation concept. Now, trustworthiness contains a lot more than that. This is one very important part, and I said explainability might be one pillar where you find the most practical implementations, and for a lot of other things, it's still debating and very much use case specific, what you can actually practically do to enhance, for example, usability or traceability or transparency of your model. Maybe one more insight in our thinking, again, coming from the research and coming from the know-how from medical AI, is how you can make models a little bit more explainable or a little bit more transparent, is exactly finding the most data efficient solution. So we are working, of course, with data-driven methods, but we sometimes might look into extracting some features with a little bit more transparent methods, as for example scattering networks and transformations and these kind of things, and then combining those with data-driven mechanisms that we are still specializing the predictions for the individual input. But we also have some parts of the model that if someone wants to really look into what were the feature extractors that we have used, that's fixed from the beginning. So you can do this kind of tricks.
Great. I hope that answered the question for the participants. Because the partners launch will be starting in a few minutes, I will just keep it to one last question. And previously with River, for example, we heard X-ray image data. It varies always depending on the machine that is capturing the image. So there's a lot of variation in there. And you showed, okay, you can also use data from variables. And now the question here is there also a high variance between the data that's gathered from the variables, so that you have to say, okay, this is an Apple Watch, this is Samsung Watch, we have to say heart rate, blood pressure is completely different, or are they close enough that you can just disregard from what device they were collected?
Yes, amazing question. Just overall, I could do this for hours. These are really very good questions. So yes, X-rays, and also we have been working in research with MRI. Depend on the machine, just by the nature of how the imaging, actually the image acquisition is happening. CT is a little bit better in that sense because it's just handful units in imaging. But to answer the question, when sometimes, for example, from these medical imaging, things about these challenges as being hard, that right, we have to make or we have to generalize the models towards different scanners. At least those scanners are doing the same thing. They might do that thing a little bit differently, but they are spitting out one image if you push the button. Well, now give an example. Yes, when it comes to smartwatches and smart devices, this is completely not true. So it's a lot bigger of a mess than those clinical devices, and can be quite frustrating. So in AI for medicine, so far we have been focusing on Apple Watch and Apple HealthKit. But I also know from different companies that we have been working with that, for example, startups that took up the challenge to deal with different devices for the same use case, basically have to step away from being AI experts into really software and full stack experts, because the synchronization, the whole APIs of these devices are completely different. So you might get kind of the same data, but you get it on different frequency, with different noise, with different resolution. And it can be very, very challenging to generalize throughout different devices. Yes.
Interesting to hear. Thanks so much, Adam, for joining us today and for the great talk. Will you be joining us for the partners launch that is happening right now?
Yes, thank you very much as well. Thanks for the questions. I can definitely stay, and I'm also happy to stay. I will bring myself another glass of water and then I can also talk.
Perfect. Then we're looking forward to seeing you in a few minutes in the partners launch. So for everyone watching, right now the expert talks are finished. And if there are any questions unanswered, or you want to talk with Adam, or you want to talk with Simona, maybe a job thesis opportunity or something else, as well as our other partners that will be joining partners launch, go to Slack channel number 0, so the channel, and there you can find a link to join the WonderMe, and in there our partners and also members of TUM.ai and the other participants will be waiting to talk with you and exchange. So looking forward to seeing you there soon. And as a reminder, there's also a password. The password is also in the Slack, and it is AI networks with an exclamation point at the end. And then please do not forget, tomorrow at 10 a.m. the official kickoff of the Makeathon will be happening, and then also the 48-hour making phase starts. And yeah, as usual, all the details will be in Slack and on Notion, and I'm looking forward to seeing you in the partners launch right now.